Today we're going to be talking about coupling simulation and AI. So it's a bit of a new topic. The prerequisite is not really to know too much about, how do you solve PDE simulations on supercomputers at large scale, but rather, can we think of when simulation and AI come together, what can we do? How can traditional AI, sort of training a model, benefit from being coupled with simulation in some sort of a loop or a workflow. And then also think about as you do, or you may start to build some of these workflows, what are things to think about when you want to apply and run these on large HPC clusters like the ones that we have here at the Argonne Leadership Computing Facility. So the lecture will cover, I would say, the sort of similar structures in the past. We'll go over, I would say, methods and best practices for coupling traditional simulation and AI. We'll start with some slides, which kind of go through motivation and different approaches and methods that you can use to create various types of coupling. And then we'll go on to two different examples. And this will all be done on the Polaris supercomputer at ALCF. And there's going to be then a homework assignment for each of those examples. The first, which we can call ML in the loop, but also sort of an active learning loop, will demonstrate a full end-to-end example of how can you couple simple simulations, in this case coming from the field of molecular design, to train a model that will help us accelerate, say, searching through a large space of potential molecules and identifying best candidates for a specific task. And the second example is a bit more technical in the sense that it's not as associated with the real application, with the real science goal, but it sets up a producer and consumer workflow implemented a few different ways, and we'll go over those implementation details throughout this lecture. But the idea here is to try to give you experience with and a way to understand when you have things producing a lot of data and things consuming a lot of data coming together, what is the right way to couple the two together, especially as the amount of data increases and as the skill of the problem increases. So as you start to leverage more and more nodes on these supercomputers. I will also mention that this material is sort of a group effort between myself, Christine Simpson, who is an assistant computational scientist in the data services and workflows group as well at LCF, and then Bethany Lush and Logan Ward, all sort of within Argonne. So with that, then I think I'll go ahead and start with the slides. If there are any questions, feel free to interrupt me if needed. But Bethany would also be available to help answer anything on the chat. So why would we want to couple what is maybe called sort of what we think of traditional HPC simulations, things like computational fluid dynamics, astrophysics, molecular dynamics simulations, things perhaps that computational science would focus around maybe 10, 15 or more years ago, with more modern methods coming from AI and machine learning. So there's a list here, but it's definitely not exhaustive. The first one, and perhaps easiest one to think of, is that we can use machine learning to substitute inaccurate or expensive components of some of these traditional simulations. So an example is closure, or what's called surrogate modeling, say that where you're trying to replace even an entire simulation with a model or an expensive component that uses, say, a PDE model or an algebraic model, and try to replace that with a neural network. Another idea would be to optimize the simulation parameters on the fly. So here we could think of doing inferencing of an AI model to select solver parameters at runtime. We could also try to couple things together into a workflow so that we can avoid some of the bottlenecks that are associated with writing large amounts of data to the file system, and then storing that data for a while. So we can do things like in situ or online training by streaming or staging data in memory. We can also do active learning. As I mentioned, that's one of the examples we'll cover. And the idea here is to sort of continuously fine-tune and deploy a model to improve the selection of training data, for example, or In this case, you could try to pre-train the model in the more traditional offline sense, and then fine-tune it with some simulation data that you didn't have access to during pre-training. And finally, we can also do some steering of simulation ensembles. So this is, for example, design space exploration or parameter optimization guided by AI, whether this with a surrogate model or with even things like large language models, as you see more next week. And the examples that we'll go through today actually cover a lot of these items, really for the exception of sort of optimizing simulation parameters on the fly. We'll really cover all of them to different degrees. And so you'll see how sort of you can integrate simulation and AI to really get the full picture of why you would want to do these things. But to give sort of maybe some schematics and give you a mental picture of how these two things, how simulation and AI can come together, there's an interesting paper that sort of tried to collect motifs for couple simulation workflows. And here are just a couple of them. So you could think of doing steering of examples where you have a series of HPC simulations producing data, and then some AI analysis or even human in the loop interaction, which then give back, feed information back to that ensemble of HPC simulations in the form of, say, input parameters or different grid refinement strategies or things like that. You could also optimize um, simulation parameters by just feeding sort of one HPC simulation into AI inference and then going straight to another simulation. Sort of similar active learning or fine tuning. In this case, you may have even experiments coupled with HPC simulations, but here you're combining analysis and training together. And then another common example, or perhaps the ultimate example of everything coming together, is something like a digital twin, where you have a combination of simulation, AI, that are trying to model a physical system in real time. So if we think about how specifically on HPC systems these two things come together, there's a couple of questions that we should ask ourselves first. So first is the type of coupling. Here we can think of machine learning inference only or training only or both. This might just basically shape the tools that we could use for this coupling or the type of workflow. So that's sort of the highest level question that we need to ask ourselves. We can then go to talking about the programming languages involved or programming models. For example, simulation is usually written in compiled languages, right? C++, C, Fortran, but machine learning is really within the Python ecosystem. So you have sort of two languages coming together, and bridging the gap isn't always easy. And ML also makes heavy use of vendor libraries like PyTorch and JAX. And so that means you're kind of stuck with their APIs and their programming model. And usually there's also different parallelism strategies, as you discussed in the past lectures. Traditional sort of MPI or domain decomposition strategies are usually the ones used for simulation, but instead, for AI training, you could have data or model parallelism of different sorts. It's also questions of whether you want to have separate components, separate binaries coming together, or trying to include everything under the same big MPI communication model. Talking about execution management, perhaps is the next thing to think about. You can stagger things in time. This is called time division. Often that means you can run things on the same hardware, but say if you have a simulation and a machine learning component as shown here in the diagram, what that means is that you would need to pause one to then make way for the other. And so things are not run concurrently. You could make some efficient data transfers in this case, but it means that there's idle time on each of the components, right? When you run the simulation, usually the ML components need to pause and vice versa. Or you could do space division, or what's also sometimes called loose coupling. And in this case, you can have components running together at the same time, as shown here in the schematic. But often what that means is that you need to sort of actively transfer and copy data from one component to the other, which can be a bit expensive. Talking more about sort of physical proximity, we can think of clustering or co-location of the compute and data. So thinking about this simple diagram on the top right of a Polaris node, so you have a CPU and 4 GPUs. If you have simulation and machine learning components trying to come together. In this case, there's also a database for staging, but that's not required. You can think of putting everything on the same node and try to distribute things across node. That can be efficient. You can see the errors here. Keep all the data transfer within a node. So that can be a scalable solution, but it's not always possible. So in some cases, you have to do what's called node clustering, where you dedicate specific nodes to the specific task of simulation or staging data or training and inference. And then finally, sort of the extreme level would be to try to do system clustering, where you dedicate specific systems to a specific component. So here, an example would be to try to use Aurora or Polaris for simulation, and then one of the AI accelerators for the ML components. Here we get into some of the more specific questions, but in terms of really, if we're trying to go after performance, data access and staging versus streaming are important questions to answer as well. Do we want really high performance direct data access? What this means is that we can, the components share the same memory space. And so this allows for, in some cases, zero copy of data between one component and the other. We're just passing pointer references, which can make the whole workflow or the coupling really efficient, or indirect, which really is a general term for the idea that each component has its own memory, so we need to copy or transfer data around. And if we need to do so, then we need to think about whether data needs to be staged or streamed. Stage is useful if the data is reused a lot throughout the workflow, and streaming is more performant, but it means that then you need to sort of handle or think about data reuse yourself within your own application, because data is really just transferred point to point rather than staged in a common area for everybody to see and read. So this was really perhaps a lot of information, but I like to go through some of these questions because it gives a picture of really some of the complexities in this space. So when users or scientists come sort of ask questions about, okay, I have a traditional simulation that I've been doing for a long time, and I'm trying to augment it with some AI and machine learning. What's the best way for the two things to come together? There's really a lot of questions, not just from the science side, but even from the sort of HPC or computer science side of how do we do this well and efficiently, and how does it scale on these big supercomputers? So the implementation choices can vary significantly depending on the different tasks. There's no one solution that fits all, but we do ask sort of these questions with scientists to understand what are the best design choices. And so the section will cover, although with sort of simplified example, but some of these approaches and some of the tools that enable us to couple simulation and AI in the ways that I've discussed. Perhaps I'll stop here for a second to see if there's any questions sort of on why you may want to do this, and then some of the complexities or some of the questions that we need to ask ourselves when coupling simulation and AI. I can't see the
So
chat,
far, nothing. Excuse me.
Okay.
So far, nothing in Slack or in the chat. So I think,
Okay.
as
Great.
folks have questions, feel free to drop them in Slack, and I'll make sure that Riccardo sees them.
Sounds great. Thank you. Okay, so this leads us to the first exercise, which I mentioned is we could call ML in the loop, or active learning for molecular design. So here we start with an actual science problem where the goal is to identify high value molecules. In this case, these are molecules with high ionization energy, which is the energy required to displace one electron from the molecule to create a positively charged ion among a large set of spatial potential candidates. And so the idea is to identify these molecules for some material design, say, or molecular design properties. But the challenge, the premise is that the simulation is too computationally expensive to run for every candidate. So say that we starts with 100,000. In this case, actually, the data set we're going to use has about 130,000 molecules, but say that we have millions or billions. So we can't just naively sort of go through them all with the simulation tool. That would just take too long. And so can we do something a bit more creative? Can we use an active learning workflow that couples a bit of simulation with then some machine learning approaches to only simulate the high value candidates and help us really sort of get to those and identify those molecules with the high ionization energy without having to do a lot of simulations? So we're going to be using a couple tools since this is sort of a workflow, right, of multiple things coming together. And so there's tools that can help us design these workflows and launch them. And in this case, we're using something called Parcel. And then we're also sort of from the molecular design space using a tool called RDKit, and then scikit-learn. In this case, it allows us to train a k-nearest neighbor model. And then the simulations are coming from a molecular dynamics package called XTB. Some of those details aren't necessarily important. We're really just going to be focusing on the workflow and how to put all the pieces together. But I didn't want to focus on this diagram here before we actually go to the code. So as you can see here, the idea is that we're starting with the blue blocks here is to do some simulation, in this case in parallel. So we're concurrently launching a number of simulations to try to accelerate the simulation process itself. Then we sort of conglomerate the data. We collect all the data from the simulations. We do a training or retraining step if we're within that active learning loop. And then we do inference, and inference means really just sort of scanning through the entire data set of molecules and trying to predict that ionization energy. We then identify the molecules that were predicted to have the largest ionization energy, and then we repeat, right? And so what this allows us to do is that we need to do some simulation up front, but then really at every loop of the iteration, we're doing a handful of simulations only just to do some retraining on those highest or most valuable molecules. Okay, so I think at this point, I'll go back to GitHub. So I did post a message in the Slack channel for this session before, but if you haven't seen that or if you haven't done that yet, before we go on to the hands-on example, I would suggest either doing a fresh clone of the repository or to do git pull origin on the main branch so that you can get the latest version of today's material. And after that, sort of as you've done in the previous sections, you want to submit an interactive job on a single node. That'll be sufficient for all the hands-on examples today. And then because we had to add some of these extra molecular dynamics packages and some of these extra workflow tools that don't come standard in the data science module on Polaris, I made a new environment for this session. And so once you do get today's material, you can just cd or so change directory to today's session. So 03 coupling same AI. And inside of there, you'll find a script called 0_activate_env. So if you source that, then you'll activate the environment that is available to everybody in the training session. And then we'll be able to run all the examples. If you're interested in specifically how that example was made, there's a link to the script or the steps to reproduce that here. Okay. So now, as mentioned, we go to the first example, ML in the loop. So some of this introductory section here I explained already, basically, in the slide. This is the same diagram that we saw, but maybe what's worth talking about is a bit just about Parcel itself. It doesn't really matter too much, I think, for this session to go into the details of what Parcel does. But one of the key features is that it allows us to effectively execute Python functions concurrently. And it builds its APIs on Python's native concurrency library, which is called concurrent futures. The idea here is that you decorate a function and then Parcel is effectively launching those functions, and it can do that concurrently, but it returns a future, and we'll see that in a second, more of what that means. And then that means that the result of the function isn't giving to you back right away, but instead you're given this future, and then you can query the future to get the status of the function, if it's running, as well as its results. So effectively, it's an asynchronous evaluation of Python functions. So the first thing to look at though real quick is just maybe this Parcel setup. There's a script here that we're going to be using, and I can open it right here. And what this is really doing is just defining the configuration for the Parcel workflow, specifically how to execute task. And so again, the details are not necessarily important of the specific executor or how the worker processes are being launched. But the idea is that because in this case, actually, for this example, we're just using the CPUs on Polaris. Perhaps the main thing to know here is that we're limiting um, the number of concurrent tasks to 32. So this is one task per logical CPU core on Polaris. And then we're giving it a set of CPU affinity. This is really just a list of all the cores available on the Polaris nodes. And then what this means is that Polaris is going to be run a maximum of 32 concurrent tasks, and it's going to pin each one of them to an individual CPU core on Polaris. So this is just something that you'll see in the example scripts that we're going to be sort of, submitting these tasks given this configuration. Okay. So then we have now, for this example, basically a series of steps, and we start to build the workflow one component at a time. So the first thing we can do is just try to launch a single simulation. And for that, we can go take a look at this Python 1 run simulation.py. So actually, I'm going to do that first here by running it so we can see the output of it, and then we can take a look at the code. So we can CD into ML in the loop. You'll see here there's 1, 2, and 3. These are the examples that we're going to cover for this particular active learning example. And we can just run it simply by doing Python 1 run simulation.py. And so it may take a while when you first run it because it's loading a lot of packages from, in this case, it's the Conda environment that I set up. But as this runs, I'll sort of go open up the file so you can take a look at it and discuss it.
As we wait, we also have one question in
Sure.
Slack. Someone asked, what's the electronic structure method used for calculating ionization energy as a benchmark? So sort of going back to what you were talking about a little bit earlier.
So that's a bit outside of my domain science element, but there is a chem functions package here that is provided within the repository. So we can take a dive into that. So if we go inside of chemfunctions.py, there's a compute vertical function. That's the one that is effectively the simulation that we're going to be running. And it's using this sort of XTB calculator to run that simulation. So I'll admit I'm not the right person to ask about the details of the chemistry calculations here. This is sort of an example that is science motivated, but the goal is maybe not to dive into sort of the actual science here, unfortunately. But if you have and are curious, you can look at this chem functions package, and if you still have questions, feel free to answer, and I'll try to get an answer for you.
Great. I think we can keep on going.
Yeah. So when we run that first simulation example, we'll see that there's 2 lines of output. The first is actually we see, we'll cover in a second, which is that when you launch a Python app with Parcel, it actually returns this future object. It doesn't actually return the output of the calculation itself. And then once we then apply the result method on it, then that's when we get the actual result. And here, in this case, it's the ionization energy of water represented with this O smile strings here, and it returns this value here. So as I mentioned, let's go back to that simulation. So you can see here, it's a pretty simple code. The only thing we have to do is really open this context of loading the parcel configuration that I just mentioned. And then we effectively evaluate what's a compute vertical application. What this really means is just parcel nomenclature to say that we took a Python function that was compute vertical, this effectively what we're calling the simulation to compute the ionization energy. And we just make a parcel Python app out of it by wrapping it with this Python app API. So we create this application, and then when we call it with the input to it, we see that it's actually returning just the future. So that's what we saw in the first output. And this is a non-blocking call. What that means is that this evaluation happens really quickly, and then Parcel in the background is launching that function to be executed on a work item, in this case on the same node that we're in, but Parcel can also do distributed execution across multiple nodes. And once we want to get the result out of that calculation, then we do this dot result method here on the future, and that gives us the ionization energy. So that's sort of a first lesson in sort of creating a Python app in Parcel and then executing it, which really requires these two steps. First, we want to call the Python app, and that returns us the future, and then we ask for the result out of that future. So this seems, for a single call like this, a bit of extra work, but we'll see actually that it's really helpful when we start to build workflows. And so for that, we can take a look at the next script that's available, which is the script called to training and inference. So what this script is really doing is that it's effectively expanding on what we saw earlier, but instead of running a single simulation, it'll actually run a number of concurrent simulations to generate some initial training for this model. It'll then go ahead and actually train the model and then run it or perform inference on the large search space of molecules. So really these sort of three steps right here. So we can go through it a bit. And then we'll run it on the terminal. So we first define the initial number of simulations to run for model training. In this case, we just set something small like 16. And then, as shown earlier, we define all the Python apps that we're going to run in our workflow. And so we already saw how to do that with this Python app API that Parcel provides. Compute Vertical was the simulation that we saw in the previous example. So we create an app for that, but then we also create apps for training and inference. So the train model and run model functions here are also given within that chem functions package that I mentioned. Training is just basically using something like it's using scikit-learn to create a k-nearest neighbor model based on the input data that's given to it. And it's using it is using a Morgan fingerprint to identify the distance between different smile strings. So also to do sort of the clustering and the distance calculation. Again, for this particular sort of the purposes of this lecture, we won't go into the details of sort of the science itself, but sort of that's a standard approach in this space. And then we have a last Python application. In this case, we're not importing, but we're just defining the function right here, and we call the Python app decorator. And this is really just since we say chunk the search space into different batches so that we can do distributed inferences, we then have this combined inferences function, which just collects everything together. So you can see it basically just takes a list of inputs and it just concatenates them into a pandas data frame. So nothing special about that. You see that we, load the search space here. Again, that's given to you in the repository. And then we start the workflow. So again, we load the Parcel configuration, opening this context. And then we go ahead and effectively do what we did before of launching a simulation. But instead of doing it just once, we do it a bunch of times. So you can see that we draw a random some smiles from that search space. So this means we draw some random molecules from that search space. And then we execute this compute vertical app multiple times, passing a smile from that string. And so this effectively, what we're doing here is we're creating a list of futures. So what we're doing here is just telling Parcel effectively all the simulations that we want it to launch concurrently. And then we have a while loop that is just waiting for each of them to be completed and then extracting the data out of it. And so this while loop is really just getting the next completed computation from the list. So here we use asCompleted, which is a Python API coming from the concurrent futures library. So this is to get the next completed future. We then remove it from the list of running tasks. And then in this case, we just get the input so that we can put it into this training data structure down here. And then if it succeeded, what we'll do is we'll just call result on that feature to obtain the ionization energy and then store the data into a dictionary which has the smiles, the ionization energy, and then batch and the time will really be used later in the active learning loop. But we also have this other alternative, which is that if the task does not complete successfully, Parcel allows us to basically submit another future to that list so that we can still make sure that we successfully completed a set number of simulations, but even if one fails, which can happen every once in a while, we simply just draw another smile string from that data set at random and submit another simulation. So once all the simulations are completed, we just store them into a pandas data frame. We then train the model, which again is really just calling that model train app, which creates a nearest neighbor model. And then we chunk the search space. This is just batching it based on the number of concurrent inferencing tasks that we can do. And then we launch a bunch of inferencing features as well, which actually pass, in this case, which is important, they actually pass a train feature and then the chunk of smile strings. This is another interesting feature about Parcel, which allows us to effectively concatenate tasks which have data dependencies. And the Parcel applications here can take as input a future of a different task. And then Parcel automatically figures out what the data dependencies are and creates the right graph so that each task is executed in the right order. But what this allows us to do is that we can launch training, and then without having to wait for the result to come back, we can simultaneously launch the inferencing tasks by just passing the train future into the inferencing Parcel application. And then finally, we create a future also for the predictions, which is just this combining all the inferencing results. Sorry, we create a feature for combining the inferencing results. And now finally, we call this result method on that. So effectively, the code will wait at this line right here until training, inference, and combining the inferencing predictions are all done. And then it'll return all those combined predictions, and then we print them out. So we can go ahead and run that. We simply do Python and then do training and inference.py. We can execute that. You'll see that we're creating an initial training set composed of 16 simulations out of about 130,000. It's submitting 16 simulations to start training. These are the smile strings that were submitted, and we have reporting on whether they succeeded or not. So here's that data structure that we accumulated at the end. So this is the training data, smile strings, the ionization energy, batch, and time. And then we saw that it started training and inference, and then it completed everything. So this, again, this training and inference completed was waiting for both training, inference, and combining all the inferencing results to be done. And that took about 5 seconds. And then here we print the inference predictions sorted by ionization energy. And so you see, of course, this is the predicted ionization energy by the KNN model. And so we see here the list of strings with their respective ionization energy. So one thing to note, which is, I think, something to be mindful about, is that we can see that actually just simulating 16 molecules here took about 10 seconds, whereas training the KNN model, which is really just passing it and storing the training data, but then really just doing inference on 130,000 of those molecules took only about 5 seconds, including the accumulation of the data at the end. So this is really one of the advantages of using some of these methods for something like search-based exploration, where we can really accelerate the task of going through a large search space with a cheap machine learning model. But this was really just still sort of perhaps traditional, not really a workflow. We just simulated some molecules, trained the KNN model, and then did inference once. So now, how do we actually then build the active learning or ML in the loop workflow? So to do that, we take a look at this next Python script called 3ML in the loop. And here we basically have the same steps as before. We start by training data by running some simulations. We then train the model using that data. And then run the model on the large space of molecules to predict their ionization energy. Except for now, we add a couple extra steps, which is that we loop back to step 1 to collect more training data, so to run some extra simulations based on the molecules that were identified to have the highest ionization energy. And then we repeat this sort of loop until enough molecules have been simulated. So to start, we actually set the random seed. This is done explicitly for reproducibility and then also helping your homework so that you don't get different results depending on when you run this and how those initial molecules for training are being sampled. So this is not something you may do in practice because you actually want some of that variability, but this is helpful for us for this example and for the homework. And then we really define the parameters of the workflow. And this is really the main things that you'll have to change when it comes time to the homework problem. So this defines the first example here, the first variable here, initial training count, defines the number of initial training samples to collect for the first training round. We then have a maximum training count, which defines the maximum number of training samples to collect overall for training throughout all the loop iterations. And then finally, this batch size is the number of molecules to simulate in each iteration of the active learning loop. So with this current setup, what this means is that we'll first simulate 8 molecules, train the KNN model, then do inference. And then at the first round of the active learning loop, we'll then simulate and retrain the model based on 4 molecules at a time for a total of 24 total molecules in the training set. So this is effectively playing with the balance of how much pre-training to do versus how much fine-tuning of the model to do throughout the active learning loop. And so in the homework, you'll get to experience with what happens when you perhaps try to front load the model and give it a lot of initial data to train on versus sort of the opposite, which is you then try to refine the model with a lot more data throughout the active learning loop. And the homework will be based on sort of trying to find what is the quickest way for you to identify the molecules with the highest ionization energy. So other than that, the script is actually very similar to what we saw earlier. I'll scroll down because this is really sort of a copy paste, with the exception of effectively this loop here, this while loop that starts the active learning iterations. And so you'll see printed here the iteration number, training, the amount of training data that you're using, and then you see that we're effectively just repeating training, inference, and combining predictions. These 3 lines here are exactly what we did in the previous example. But now we're going to sort the inference predictions and basically pick out the best candidate molecules. And then we're going to simulate those at the bottom here. You can see that we are, sorry. In this code block right here, we're going to effectively launch a number of more additional simulations. We're then going to wait for them to complete, compute just an estimate of the error, since it's not a lot of data, but it's helpful to just keep track of it. And then augment the training data with what we just simulated, and then just repeat the loop. So if we go run that on our terminal, it should start up pretty quickly. The first output will look pretty similar to what we saw earlier. You'll see that in this case, we're collecting a maximum of 24 training samples, as we mentioned, and we will run 4 new simulations in each loop iteration to refine the model. So we're starting with those 8 molecules picked at random. We submitted those 8 simulations to create the training data, and then we start the active learning loop. So at iteration 1, we had these 8 random molecules and then to train on, and the output here gives you the best molecule, basically the molecule with the highest ionization energy according to the KNN model prediction. But then you see here that based on that batch size that we mentioned, at iteration 1, we then performed 4 new simulations and then moved on to training to iteration 2, in which case we had now 12 training data samples for training. And you can see that what that does not the second loop, but the third time around when we've now training with 16 data sets that allows us to actually predict a different molecule with the highest ionization energy. In this case, is just slightly higher, but actually as we start accumulating more and more training data, and specifically training data of molecules that have high predicted ionization energy, we see that finally at iteration number 4, we can predict a new molecule with pretty sort of a significant jump in that ionization energy. So at the end of the script, what it does is it just makes a plot. So I'll go down to the README here, and it makes a plot like this, which is basically just a plot of the ionization energy of the predicted molecules as a function of either the loop iteration or the compute time. So it is effectively sort of, and then sort of plots the step function, which is effectively plotting, if you see here, it follows basically this highest ionization energy prediction here that is being reported by the log. So I'll stop here to see if there's questions, and then I can describe the homework. Okay, so then for the homework, really what we're wanting you to do is to play with those parameters that I mentioned that define effectively the balance between pre-training and fine-tuning of the model to see what is if you can identify molecules with the highest ionization energy possible, but in the quickest or shortest possible time. So effectively what that means is that you can either run that the 3ml in the loop Python script that I just found, or you can use this submit script here, which effectively allows you to, if you want, to submit the workflow on multiple nodes. But you should really try to play with these 3 parameters here to figure out basically how quickly and how well you can train this k-nearest neighbor model. In terms of submission, really all you would need to do is submit this updated README and in your code, where the plot of your best result should be just uploaded automatically here at the bottom of the README file. So you'll see it if we discuss this plot here on the right for just a second, that you see initial results get plotted around 15 seconds. So that's the time that initially took to simulate those initial 8 simulations. And then based on that batch size, that sort of determines the gap here between subsequent results. And so as you play with those numbers, you can either try to see if you can get better predictions right away by simulating more data, or instead doing more of those active learning loops and how much data to use in that active learning loop. That's really going to be sort of the crux of the homework. Okay. So then in the remainder of the time, I want to go to the next example. In terms of observations, I think I covered these all as I was going through the hands-on, but I added a slide just to make sure that some of the takeaways were being marked. So exercise 2 sort of takes perhaps some of these ideas or some of this workflow implementation to a bit of a next level. Specifically, the machine learning in the loop that we just looked at relied on relatively small amounts of data, right? Sure, we had a lot of molecules to screen, but in terms of size of the data, we weren't really dealing with, gigabytes or terabytes of data. And so what happens to some of these workflows when we really try to scale up the size of the data or even the size of the problems? So instead of running everything on a single node, what if we have to run things on hundreds of nodes? And so to sort of try to understand some of the bottlenecks and some of the issues that we encounter coupling simulation and AI as the problem scales up, let's just consider a producer-consumer workflow. And in this case, it's just a simple workflow to try to train a machine learning surrogate. So on the producer side, we really just have an ensemble of toy simulations that are just advancing the 2D wave equation on an n by n grid and produce training data for each of these simulations, which is a series of pairs of the solution at time step t and then the solution at the next time step. So we have sort of a workflow process similar to what we saw earlier that is launching concurrently a number of simulations, each simulation with slightly different input parameters, for example, the frequency or the period of this wave. And then each of the simulation is producing training data, which is the pair of sort of, one time step and then the next time step, um, all accumulated together. So then the next step would be to collect all that training data. Here's sort of a representation of how that data would stack up from simulation one. You would have U1 at time t, and then U1 at times t plus delta t, et cetera, et cetera. And then same for U2, which would be solution coming from simulation two, and so on. And then on the consumer side, we can think of this to being an ensemble of model training. In this case, we chose a convolutional neural network to do another regressive task, which is to effectively say if we can train a convolutional neural network to replace the simulation itself. So can we pass the solution of the wave equation at one time step and have the convolutional neural network give us the solution at the next time step? But we launch an ensemble of these CNNs to sort of emulate what we would do in a practical application, which is to try to run a bunch of instances of these models with different hyperparameters, such as the architecture or learning rate or batch size, et cetera, to understand what is the best way to train this model. And then finally, we want to collect all the models to evaluate them, maybe in some validation set or some test. So this is sort of the setup. Now, if we think of the parcel implementation that we just saw, as the data scales up, that really poses some bottlenecks. Specifically, the way that parcel, sort of the way that the machine learning in the loop example was set up, is that it was using these Python futures and then basically transferring data through what are really Python multiprocessing pipes, or in the multi-node case, these are actually TCP communication through things like CRMQ. But the sort of the key point here is that implementation, which requires spawning a bunch of simulation and tasks, and then collecting all the data back to effectively a head workflow process to collect the training data, and then sending that entire training data set to then all the training instances. As we'll see in a second, as the data size grows, it can really slow down the progress. So this idea of this concurrent future implementation, as I mentioned, relies on TCP transfer, which can be fairly inefficient for large data. And we won't see this particularly in this example because we won't go to such large data sets, but you can actually run out of memory at a certain point if you imagine a lot of these simulations, each contributing a lot of data and then collecting it all on a single node. There's only so much memory on a node. So then the next thing we could do, or the next sort of the immediate next step, would be to use the parallel file system. And so this actually does alleviate that bottleneck quite a bit, as we'll see in a second. In this case, we can have each simulation writing its own data that it's accumulated through its runtime to its own file. And so we can produce one file per simulation, say for a total of n sim files for number n sim simulations. And then what we would do is that each training instance now reads all the data from all these simulations. And so now we can have n CNN processes, so as many processes as model training instances, trying to read n files. And so you can see, I try to sort of draw that with this little schematic, that what happens, especially as you go to large scale, where you have more and more of these convolutional neural network instances running at the same time, is that the file system then itself can become a bottleneck as well, because you have a lot of processes trying to open and read data from the same files. And so specifically that can cause an issue with the metadata server contention of the parallel file system, effectively by having too many concurrent file open and close operations. But in general, if we really go to a lot of nodes, we would even run into just the bandwidth limitations of the parallel file system, which for Polaris and the Eagle file system, it's about 650 gigabyte per second, which seems pretty high. But if you're running on all of Polaris, that bandwidth itself could be a limitation, not just sort of the amount of concurrent open and close operations, but just reading data from the file system fast enough. So what can we do? So this is where we introduce something that is an interesting solution that a lot of applications have been using on our systems to alleviate effectively the bottlenecks of either using things like TCP connection or concurrent futures or the file system. And they're leveraging things called sort of as a whole distributed in-memory key-value data stores. So this could be a distributed dictionary coming from the Dragon HPC tool, as we'll see in a second, but it could be something a bit more basic, something like a sharded database such as Redis or MongoDB. And the idea here is to really, instead of going to the file system, you can enable fast storing on the node's memory effectively, but doing that on a distributed fashion. So instead of having data that's sort of uniquely tied to each node, these distributed dictionaries or this sort of in general distributed in-memory key value stores allows to effectively have a distributed view of all your nodes' memory. And instead of going to the file system again, you can have fast I/O directly to the node memory. And if you do need to access data on other nodes, a lot of these tools give you fast data transfer across the interconnect. Some tools do TCP only, which isn't very efficient, but other tools do RDMA, or you could do some other implementations with MPI. And in some cases, not for this example, but in some cases, you can go to that co-location of data and compute that I mentioned at the very top of the slides, which really avoids any internode transfer. And in those cases where that's possible, it really leads to really fast and scalable solutions for coupling simulation and AI together. Okay, so now let's go to that second example, which should be quicker, because really what we're trying to do is just set up a toy simulation, as I mentioned earlier, that's really just advancing the wave equation. So it takes in a period of the wave and a grid size, sets up a grid, and then for 10 time steps, iterates through and updates training data where the inputs are the solution at one time step and the output is the solution at the next time step. And then, as I mentioned, we're trying to train an autoregressive convolutional neural network. For the purposes of this, just to make the examples run quickly, we have a very simple convolutional neural network. It's actually just 4 layers. And the idea is again, to predict the next time step. So effectively replace the simulation. And the trainer is also very simple. It just takes as an input the kernel size, just so that we can do or sort of emulate that hyperparameter tuning that I mentioned earlier. So we actually instantiate, you can see here, we instantiate the convolutional neural network with different kernel sizes based on what we pass to the trainer function. And then we just simply do one epoch of training based with a mean squared error loss and add an optimizer. The crux of this will really be sort of in these lines, which is how do you get from all these training instances, how do you get the simulation data that was produced by that ensemble of simulations? And so we're looking at 3 implementations of this workflow. The first is implemented in Parcel using concurrent futures, as we saw earlier. So I won't go through this sort of implementation because it's really following what we saw earlier, where we're trying to create Python apps of the simulation and trainer and just launching them, creating a list of futures, and then grabbing the results later. But we'll execute it and try to get a sense for how long does it take to do that computation. So actually, let's go do that now. So we go to the producer consumer directory here. You'll see we have here a set of example scripts. And to start off, we run this Parcel implementation using the futures here. So this I'll actually run twice, just because the first time the trainer takes longer than normal, just because we need to warm up the GPUs. So the training process takes a bit longer, but we'll get back to that in a second. So the second implementation uses Parcel as well, but as I mentioned, it writes things to the file system. So instead of returning the data through the future and then having to accumulate it all on that head process of the Parcel workflow, we instead just write to the file system, and the training instances just read from the directory where all that data was stored by the simulation. And the further implementation uses Dragon. For that, we'll take a look at the code. But what I wanted to highlight first was just to get a sense for the time it takes to do these two different implementations of doing things through futures versus doing things through the parallel file system. So you see that we launched 32 simulations on 32 workers. So in this case, we have one simulation running per CPU core of this Polaris node for a total data size of 0.6 gigabytes. So not even that big. And we see that that took about 14 seconds to run. And now we're running 4 convolutional neural net model instances to train on that simulation data. Again, this is passing different values of that kernel size, so it's sort of effectively emulating a hyperparameter tuning operation. You can see how long that's taking already, right? Even though it's really just less than a gigabyte of data that we're trying to transfer to the training processes, you see that in this case, it took about 85 seconds. A lot of that was actually passing the training data itself. But some of that was sort of the first iteration of training always takes a bit longer than usual. So we'll run it again just to get, say, a more a fairer estimate of how long it takes to do this training step here. So you see simulations took about the same time, about 14 seconds. And this should be quicker now. It's maybe about 20 seconds. Right. So talk about 26 seconds. Now, if we then run the next example, which is using parcel, but now passing things to the file system, we'll see the difference here. So again, we're doing the same exact thing. The workflow is set up in exactly the same way, but now we actually can time the time spent doing I/O to the file system, and we see that we were able to overall accelerate how quickly the simulations were done. But really, the I/O time here is less than a second, so really fast. And then similarly, you can see how much the training was sped up. So again, this is the same amount of data, so the trainers are doing the same amount of work. Really, the difference here was in how quickly we're able to load that data from the parallel file system compared to instead, as we saw in the slides, accumulating all the training data on the head process of the workflow, and then sending that data, serializing it, and then sending it, in this case, through pipes, or if you're doing a multi-node instance of this, through TCP communication to all those trainer instances. So significant improvement there. Now, let's take a look at the Dragon implementation of this, since that is a bit new. So first, we just look at a simple script that just sets up the Dragon dictionary and then sets up a simple toy function. So this is sort of an introduction, a quick introduction to Dragon. So what Dragon does, Dragon HPC, is that it's an open source tool, which is really, I would say, has 2 key characteristics specifically for this topic. The first is that it's effectively a multi-node extension of the traditional multi-processing library in Python. So everything like, for example, pools or an MP process or an MPQ that you would do, say, on your laptop, or that you could do on a single node on a supercomputing cluster. With Dragon, you can now do that on multiple nodes. So you can set up a pool similarly to Parcel effectively, where you're launching a function, but you're doing that distributed across multiple nodes. And really all you need to do to access that functionality is to set the start method of Python multiprocessing to Dragon. And then the other feature, which is interesting, is this distributed dictionary, which I mentioned, this distributed key value store. And to do that, we really just need to initialize the dictionary with their pdict API, where we pass some information, which is not particularly essential for the purposes here, but you can play a bit with the managers per node. This allows you to get a bit more performance because you have multiple processes sort of dealing with requests to and from this dictionary. You give it the number of nodes that you want the dictionary to span across, and also the total memory that you want this dictionary to pre-allocate, basically. So you reserve some memory aside for this dictionary for you to then safely write and read data from it. But from Python, this dictionary, as I mentioned, is really, it's a really attractive feature, because what it means is that you can access it really just as a Python dictionary. So for example, here we can add some input data. We do the distributed dictionary. We give it the key input and then the value hello. And then we run this toy function, passing the dictionary through the function argument here, which takes the input data that was previously stored by the head process and then just simply adds from the toy function that string to the input and then puts it back as an output. And so finally, then we see at the bottom that we can print the result of that operation, and you'll see it'll be the combination of this input and the output data added by the toy function. The other thing to mention is that when you're running Dragon scripts, these are just Python scripts, but they must be run with the Dragon executable. So instead of Python and then the name of the script, you just need to say Dragon and then the name of the script. And so we're running that, and you'll see that it's some information here telling you Dragon is running on, in this case, just one node, and it's printing the node name. It started the distributed dictionary on one node with just a few gigabytes of memory in this case, and then it's printing hello from the toy function, sort of the output of what we just saw in this little example. But what is, of course, more interesting is then taking a look at the producer-consumer workflow implemented in Dragon. So the main script actually starts in a very similar way. Here we're just parsing some arguments, command line arguments, to specify the size of the problem, specifically how many simulations and the grid size for those simulations, so effectively how much data to produce. We initialize the start method for multiprocessing to Dragon, get some system information, as I mentioned, so that's what gets printed in terms of the number of nodes it's running on and the node names, etc. Initialize the distributed dictionary. Again, in this case, for performance, we have a few more managers per node than that initial example, and we also give it a bit more memory. In this case, about 30% of the available memory on the Polaris node. And then really what we do is we launch, fairly similarly to what Parcel was doing, using a Dragon pool, which is just basically an extension of the multiprocessing pool. We initialize it. In this case, we do a trick here to pass the dictionary instead of through the argument, through this initializer function, which makes it a bit more efficient. And then with pool map async, we effectively pass, we call that simulation function here that I talked about earlier, passing the arguments to the simulations. And again, for a Parcel future, we would call result, and here we call get to get the results back. So we do that for the simulation, and then we do that for training. So fairly similar, but what I wanted to then show is what happens when now we run, the workflow, this producer-consumer workflow implemented in Dragon HPC. So again, here we'll see that the dictionary is just running on one node again, but in this case, we're giving it more memory, about 150 gigabytes for this one node. We launched 32 simulations on 32 workers. We were again, and we set up the Dragon workers, the Dragon pool, to take as many workers as there are maximum number of CPU cores on Polaris node. And we're generating the same amount of training data. So you can see here a couple things, especially when we compare it to this run above here, which was the Parcel implementation with the parallel file system. So the simulations actually took less time. It was about 11 seconds for Parcel, and it's only almost a bit under 7 seconds for Dragon. This has more to do with the efficiency of Parcel versus Dragon in terms of launching these processes. Because if we look at the I/O time, which in this case was to the parallel file system, and in the case of Dragon down here, it was to this Dragon dictionary, we actually see that in this case, the parallel file system is a bit more efficient. And similarly, on the trainer side, we see that there's a bit of extra overhead, which some of it is coming from, although not all, but it's coming from um, the larger time that it takes to get all that data that was put into the distributed dictionary from the simulations out um, to the training instances. So this was sort of the way that the scripts are set up on a single node. And this was actually intentionally set up to sort of demonstrate what you would do on this moderate scale, where you have, just about a gigabyte of data, and you're really just running things on a single node. What we see in terms of the key takeaways is that actually the parallel file system can be an interesting solution for these, I would say, intermediate cases, right? We saw the initial implementation with parcel futures takes a really long time, and you'll see as you explore the homework and you increase the amount of data that the future implementation with parcel becomes quite inefficient. The parallel file system, however, can be a good solution at this scale. But what you'll see in the homework, which encourages you to try these scripts on multiple nodes, you'll see pretty quickly, even just on 2 nodes, that the Dragon implementation becomes more efficient. And so that's what what I was mentioning earlier, which is really that metadata server overhead taken over for the parallel file system implementation as you have more and more of these training instances trying to read the same data at the same time. So going back then to the README for this particular example, there's some run instructions here, which covers what we just did, but then we go on to the end, the homework problem. And so here, what we would like you to do is using the parcel and Dragon implementation of this producer-consumer workflow, fill in this table below, which was really trying to sort of get you started on the idea of exploring how these different implementations perform as you scale the training data up in terms of number of size, as well as scale up the workflow in terms of number of nodes. So you can use what's being reported in the log files that we just saw to fill in this table right here. And to increase the size of the training data and scale up the workflow, you really just have to do a couple things. So the workflow scripts take in this number of simulation argument and this grid size argument. So by increasing the number of simulations and the grid size for each simulations, that's how you can generate more data from each simulation. And then using this submit script here, 9 submit multinode.sh, you'll see that it effectively runs through all 3 of these implementations, but you can change the number of nodes on which to submit the workflow on. And so here are some notes on just sort of how to do that, just so that you have it when it's actually time to run the workflow and where to sort of grab the data as it's being produced by these scripts. And then the last thing, really just write a short paragraph on your observations. Really here, the questions that we're after is sort of what implementation is best as the size of the data and the size of the problem in terms of concurrency of simulations and training tasks. How do the different implementations perform as you play with those numbers, and whether that matches your expectation or not in terms of writing things to the file system or doing things in memory. And so that's really it. Yeah, these were some of the observations. I can stop here if there's any quick questions, but I realize I'm running a bit over into the next session of the lecture. And of course, I'll be available on Slack to help with the homework or anything that we weren't able to cover right now.
Great. Thank you, Riccardo. As you just said, if there are any questions about today's session or as you work through the homework, please ping on the Slack channel. But I think for now, we will say thank you to Riccardo and move to our science speaker for today. Our science speaker is Thang Pham. Thang is a PhD, is a postdoctoral researcher in the computational science division at Argonne. His research focuses on agentic AI frameworks that integrate molecular simulation, machine learning, and high-performance computing to accelerate materials discovery. He earned his PhD in chemical and biological engineering from Northwestern University and his bachelor's in chemical engineering from Worcester Polytechnical Institute. Today, he's going to be talking about work that he's been doing on an application called ChemGraph. ChemGraph is an agentic framework for computational chemistry workflows, and I'll let him introduce it a little bit more from there.
Thanks, Pitch, for the kind introduction. Can you hear me well and can you see my screen?
Yes and yes.
All right. All right. So let's begin. Hi, everyone. Today I'm going to give a talk on our application that we developed recently called ChemGraph, which is an agentic AI framework for computational chemistry workflows. First, I want to briefly talk about large language models and agentic AI. I'm sure the audience have been familiarized with large language model and use them throughout your research as well as your daily life. The typical way that a human interact with a large language model is that we send a prompt in the form of either a query or a comment or a question to the large language model, which will process that prompt, given the context, and give the user an output. A common problem with large language model is that because it relies entirely on its internal knowledge, a lot of time it hallucinates, or in other words, it produces answers that are plausible but are really incorrect. And that poses a challenge when you want to put all this large language model into your research workflow because you don't know when or how it may hallucinate. A way to reduce the chance for hallucination is providing large language model with different tools capability that allow the large language model to instead answer you based on its knowledge. It can invoke these tool calls to produce an output. A simple example for tool code you can imagine it's the web search tool that are available on a many platform of large language model nouns, where instead of LM just give you an answer, it goes through a web search and analyze the data from the web search tool called to give you an answer. Another example can be as simple as a calculator. So instead of relying on large language model to do math for you, the large language model can actually invoke different calculators and input the expression that the user want and give the user a correct answer. Here's my favorite example for when large language model hallucinates. Given a human's question on when a human asks to provide a SMILE string, which is a text representation of a molecule, to a good large language model like GPT-4, what we often see with large language model is that it will try to reason through the question and give the user an answer. And a lot of time, as in this example, this answer is incorrect. In this work, we introduced ChemGraph, which is an agentic framework that gives different tools to the large language model to solve this problem. These tools that we define here range from cheminformatic tools, things like converting molecule name to SMILE string, to actually running and performing molecular simulation across different domains, things from semi-empirical method like XTB to density functional theory calculation, as well as the more recent machine learning into atomic potential. Within ChemGraph, it can operate in two modes. One, it can just give you a regular output, similar to a human-like text that the large language model often gives you when you ask it a question. Or it can also create a structured output. Basically, the answer will be something in a JSON format that could be further processed in your downstream application. Now, given these tools that ChemGraph has, it can solve the problems that the traditional, just the large language model cannot solve. Here's an example when you put this question into ChemGraph using a worse model than, which is a GPT-4 mini. Instead of trying to reason through this question, what it does instead is that it invokes the tool call that we give to it. The tool name here is molecule name to SMILE with an argument of the molecule name. And this tool will produce an output that the large language model will report back to the user. And because it relies on the tool call instead of just relying on its internal knowledge, the SMILE string that it gives agree with what we would expect from getting it from database like PubChem. That was a very simple example, but now we want to make sure that ChemGraph work across a wide range of tasks. So what we did in this work was that we developed a data set consisting of 360 different benchmark tests that cover more than 200 different molecules to evaluate the performance of different large language model within ChemGraph. These tasks can be as simple as converting molecule name to SMILE string that I showed you in the previous slide, and or it can get to more complex tasks like calculate a reaction enthalpy or reaction Gibbs free energy for a given chemical reaction. What we saw in this work was that when we look at proprietary model like GPT-4 Mini and Cloud 3.5, they all perform very well with an accuracy of above 80%. The only open source model that we benchmark this work when perform well, but for certain tasks it does fail with a accuracy of about 60 to 70%. A common theme between these three models is that when it gets to a more complex task, like calculate reaction enthalpy and reaction Gibbs free energy, you can see that the performance or the accuracy of this large language model drops significantly. Even for a model like GPT-4, even though the accuracy is relatively high, above 80%, but if we want to put this in computational workflow, we are probably not satisfied with an 80% accuracy. What we did to improve ChemGraph was that we introduced a system of multi-agent in which instead of a single agent that process all the two core and all the reasoning, we kind of distribute this task among different agents. We have a planar agent that decompose the user's question into smaller subtasks, creating smaller subprompts that send this prompt to an executor agent. This executor agent will have access to the tool similar to what we discussed for the single agent case. And once all these executor agents finish their two code, the result will send to an aggregator agent that synthesizes a final answer based on the original question, the planners, as well as the result from the executor agent. Here's another example of how human would interact with ChemGraph and specifically the multi-agent version. In this case, the human wants to calculate the reaction enthalpy for a methane combustion reaction using a certain computational method at a certain temperature. What happened at the planar agent level was that the planar agent will decompose this task from the human into smaller subtasks, basically calculate these properties of different molecules, every individual molecule. And after the planar agent finish creating these smaller subtasks, these are sent to the executor agent that invoke these two calls to get the output, which are the properties of individual molecules. And given the original human question, as well as all these two output, a final aggregator agent can synthesize an answer based on the results that it observed. When we compare this single agent to multi-agent performance, we saw a huge boost in performance in terms of accuracy for the two tasks that I mentioned earlier, where the single agent seemed to fail. For GPT-4 Mini, the accuracy increased from roughly 40% to over 80%. Very similar behavior we observed for Cloud. What it's interesting is that given this multi-agent and a good model like GPT-4, the agentic system actually obtained a accuracy of 100%, meaning that it always get the answer correctly for the users. And as I highlighted earlier, when we want to put this agentic workflow application onto HPC and run on HPC, we want to observe an accuracy of 100%. In this work, we also provide the user interface so that people can interact with ChemGraph via just simply chatting with the agent. So you don't have to launch a Jupyter notebook, but simply chatting with the agent, similar to how you would interact with other large language model like GPT-4. Finally, I want to briefly mention the capabilities, the things that are already in there in ChemGraph, as well as things that we are trying to develop. And we're very open to collaboration and help you with developing similar agentic system for different domain science. In terms of simulation engine, ChemGraph can handle different simulation methods from DFT to the foundation models that I mentioned earlier, as well as the different multi-color simulation code. A lot of time with chemistry and material science, it's not just about launching simulation. A lot of time it's also about how a human would visualize a certain molecule or certain materials to make certain decision. So in this case, we are working on a project to have agentic system in combination with multimodal intelligence, particularly looking at constructing molecules and different materials using ChemGraph. We're also looking at using ChemGraph to orchestrate portrait simulation on HPC, things such as job submission, as well as running parcel. The code is open source around at ALCF, and we are happy to collaborate with students and people who are interested in agentic workflow. So with that, I would like to thank you for your attention. I'd love to take any questions.
Thank you so much. So any questions for Thang, please drop in the chat. I think, meanwhile, can you talk a little bit about sort of the scale of something like this? I'm thinking like, is there like a limit on the number of tools that you can add to an agentic model like this? How can you, is there, and sort of like, what's the capacity for generalization? Obviously, ChemGraph serves mostly just chemistry, right? But is this a way, could you like theoretically scale this to all of the physical sciences or even beyond that?
Thanks. That's a great question. I think we love to generalize it, but the amount of tools that it can has, it's depend on the large language model. So when you pass a tool to it, start filling up the context window of a large language model. And the more tools that you give to it, we would expect the performance to start at a certain threshold, you start seeing it dropping. So right now, what we're seeing, it's kind of compartmentalized different science domain with different agentic model, rather than having, a one chatbot that solve everything with a multiple smaller sub-agents that handle different domain science.
That makes sense. And a question from Slack. What methods are used to benchmark accuracy for DFT and others?
So we create a synthetic benchmark. Basically, let's say if you're human, it's posed with the same question. What are the two calls that a human would call to solve a particular question? And that would be considered as a true answer. When we benchmark this large language model, we just pose the same question to the large language model and look at the accuracy or the list of two calls that the large language model invokes. So that would be and just compare the final answer. So that would be how we determine accuracy.
Great. Another question. How much time do you invest into prompt engineering comparing against those of agentic workflow engineering? And do you think like what's the relative importance for this?
I think prompt engineering it's very important, but we actually didn't spend that much time with prompt engineering. The prompt engineering for me is mostly to tell large language model to rely on tool call instead of using its knowledge. So basically tell it to you have to call tool. It's a little bit more elaborate than that, but it's not like you have to fine tune for each of the tool or anything like that. It's more like tell the large language model to use the tool that we give it.
Sort of as a follow-up, does that mean like if you're using something like a ChemGraph, as a user, it's helpful to sort of know what tools you might be able to query in order to actually be able to use it instead of just like going in and sort of asking a chem question kind of blind?
Yes, that's correct. So the current limitation would be the tools that it has. So you should know ahead of the time what kind of tools does ChemGraph have and can it do.
Great. Looking if there are any other questions in the chat. I don't see any more right now. Can you maybe talk about in the final minutes that we have any challenges that you had as you were building this model, like any surprises as you sort of built things out?
That's a great question. I think there are always things that you don't foresee beforehand. Um, um, we were actually a bit surprised how well this large language model is at coding tool. Um, going back, I think a couple of slides ago, you can see that with our design in GPT-4, it can solve all the problem within the tool that it has, 100% accuracy. So and even with the other model that are much smaller, like GPT-4 mini or cloud, it actually solved it with pretty high percent accuracy. So that's something that we were quite surprised at the beginning. Um, yeah.
Yeah, I feel like 100% accuracy is, you always like, is that real in science, right? Anytime it's going perfectly. Um, so maybe one final question before we wrap up. Um, so you mentioned that obviously this code is open source, but I guess as a user, how might we sort of go and interact with the model itself? Do you have a web interface that you've been building? Is
Mhm.
this open and ready for chemists to go and use?
Um, that's a good point. I think we're in the process of trying to make it available to ALCF users. But right now, it's only the code is available, so people can go in and try it. Uh, and yeah, it's in progress, I would say.